Welcome to Lesson 4, Part 1, where we will discuss several methods for measuring surface and ground fuels in the field. In this lesson, we will review the definition and classification of down-woody material. Then we will discuss two methods used to inventory surface fuel loading, including their advantages and limitations. We will guide you through the steps of each of these methods by providing hypothetical scenarios for practice. Finally, we will end with a conclusion and short review. Most of you are probably already familiar with downwoody debris, but we're going to go through a quick overview. Downwoody material refers to all woody material larger than litter produced by trees or shrubs. This includes all twigs, branches, trunks, and boles of trees. Downwoody material can be both on and above the ground. For example, branches on a tree that has been windblown to the ground count as downwoody material, even though the branches themselves may not be on the ground. Downwoody material is generally broken up into large classes: natural debris and slash. Natural debris is the natural accumulation of fuels. Slash is woody debris from a harvesting or thinning process. In the next slides, we'll learn how to adequately measure downwoody material. The most common fuel assessment method for measuring downwoody material is the work detailed in Brown 1974. Brown's approach uses a planar intercept method to inventory the weights, volumes, and depths of downwoody debris. The technique is used based on work conducted by Van Wagner of 1968 and allows for an inventory of fuel loading by weight of both small and large woody fuels. These methods, or modified Browns, are commonly used in the Forest Service, National Park Service, and in research. Brown states that planar intercept method can provide the following information. 1. Weights and volumes per acre of downwoody material for all diameter size classes. 2. Average diameter of debris larger than 3 inches. 3. Depth of fuel, litter, and forest floor duff. This method estimates the volume of forest fuels and then calculates a weight by applying estimates of specific gravity. In other words, you count the pieces of each time lag class and then use equations to determine weight in tons per acre. The planar intercept method has two advantages. First, it does not take much time to complete a plot. Brown estimated it takes between 5 and 6 minutes, or 20 to 40 plots per day. Second, this technique is non-destructive. This method assumes that woody fuels are randomly oriented and randomly distributed over the study area. As we know, this is not always true for an area. Employing the planar intercept method is quite basic and requires 4 steps. The first step is to choose a site to inventory. For the second step, decide the length of the sampling plane and the number of sampling points. We will see how to do this in the next few slides. The third step is to complete the measurements. The last step is to use the measurements to complete the calculations. This chart shows the field equipment generally needed to take measurements using the planar intercept method. When choosing sampling plane lengths, Brown 1974 suggested basing lengths off the type and diameter of downed material. In general, 15 to 20 sample points should be located to reach a percent error of around 20%. Areas larger than 50 acres or areas with a high diversity in the amount and distribution of downed material should be sampled more intensively. The USDA Forest Service Common Stand Exam Field Guide expanded Brown's table to include percent errors from 15 to 35% and the number of sample points from 5 to 30 for different diameter fuels. For example, using the table above, suppose we require a standard error of 20% and we plan to sample at 20 points. Looking at the number of sample points column under 20 and following it down to a standard error of 20% for each diameter range, we would need to sample fuels less than 1 inch for 8 feet, fuels between 1 and 3 inches for 12 feet, and fuels greater than 3 inches for 50 each along each transect. Many different sampling protocols can be used to locate the sampling points. The most common methods include systematic sampling, simple random sampling, and stratified random sampling. To conduct systematic sampling, you start by randomly selecting the first point on the ground. Then you establish plots at a given uniform spacing throughout the area. Two advantages to using systematic sampling in fuels inventory are that the units are easy to locate on the ground, and the units appear to be more representative since they are uniformly spaced over the entire area. Systematic sampling assumes that the population is randomly distributed across the landscape. However, in cases with a periodic variation on the landscape, it is possible that the systematic sampling will not capture the true variation. For example, see the figure labeled 8.2. The sampling method does not capture the periodicity of the landscape. In cases where little information is known about the basic characteristics of the sample population, like variance, it is better to use a random sampling technique. The first type of random sampling is simple random sampling. Simple random sampling means that every possible combination of sampling units has an equal and independent chance of being selected. In other words, the selection of one point is not influenced by the selection of any other point. This type of sampling design is common and is assumed in many statistical tests. In Figure 8.1, an example of this type of sampling is shown in the lower left grid. The second type of random sampling is stratified random sampling. Stratified random sampling involves dividing the population or area into subpopulations of known size and sampling within each subpopulation. Avery and Burkhart, 1994, state the following. If the strata are constructed so that their averages are different and their variances are small in relation to the total population variance, the estimate of the population mean will be considerably more precise than that given by a simple random sample of the same size. Also, it may be desirable to have separate estimates for each subpopulation. For example, if we were sampling a 150-acre piece of land for fuels, we may notice that 1/3 of the land is ponderosa pine, 1/3 is mixed conifer, and 1/3 is aspen. In this case, it would be a good choice to sample using a stratified approach, since we can assume that each of these may have very different fuel loadings. In Figure 8.1, an example of this type of sampling is shown in the lower right grid. For our purposes, just remember that any of these sampling techniques is a viable approach to fuels inventory and that they all have advantages and disadvantages. So how can we do this in practice? The first step is to mark a sample point. Take care to avoid disturbing the area around this point. If measuring standing trees also, complete planar transect measurements beforehand. The second step is to determine the direction of the sampling plane. Many options can be used to randomize this. For more information, see Brown, 1974. Be sure to avoid biasing the placement of the transect. The third step is to run a measuring tape the length of the sampling plane. You should determine this length prior to going out in the field. The fourth step is to measure or estimate the slope to the nearest 10%. Step 5 is to tally the number of particles that intersect the sampling plane by size. Recall that the size ranges are 0 to 0.25 inch, 0.25 to 1 inch, and 1 to 3 inches. Step 6 is to measure or estimate the diameter of all pieces that are 3 or more inches in diameter, which intersect the sampling plane. Record diameters separately for rotten and non-rotten logs. It can also be helpful to estimate the species, length, and decay class for large woody debris. Step 7 is to take 3 measurements of dead fuel depth. Record the depth as the vertical distance from the bottom of the litter layer to the highest intersected dead fuel particle at 3 locations along the plane. Step 8 is to measure the vertical depth of duff at 2 points. This measurement is typically located at 1 foot from the plot center and then between 3 and 5 feet from the first measurement. If trees, logs, or stumps occur at the point, you can offset 1 foot perpendicular to the right side of the sampling plane. The final step is to record the predominant species for the entire sampling plane. If several species exist, estimate the proportion of the 2 or 3 most common species. Note that the planar transect is not just with the measuring tape on the ground. It must be thought of as a plane approximately 6 feet tall, and all material from the ground to 6 feet is included in the count. When tallying fuels particles, consider the following rules. In general, dead branches attached to standing trees are omitted. Cones, bark flakes, needles, leaves, grass, and forbs also do not count. Additionally, if the particle lies in the duff layer where it intersects the planar transect, it is not counted. Additionally, if the sampling plane intersects the end of a piece, you should tally only if the central axis is crossed, and if the sampling plane intersects a curved piece more than once, you should tally each piece. You should also tally wood slivers and chunks left after logging. Visually mold these pieces into cylinders to determine size class or recording diameters. And finally, tally only uprooted stumps and roots that are not encased in dirt. Do not tally undisturbed stumps. There are 2 equations used to calculate fuel loading in tons per acre when using the planar intercept method. The first equation is used for all fuel size classes less than 3 inches, so 1, 10, and 100 hour fuels, while the second method is used for fuels over 3 inches. The 2 equations are very similar with the exception that the second requires the user to sum the square diameters. Brown 1974 provides tables to help users calculate the slope correction factor, the non-horizontal angle correction factor, and the specific gravity. For our example, we will use a data set of 4 planar intercept transects collected from a Douglas fir stand in Central Oregon. All transects were on slopes less than 10%, and all of the 3-inch fuel was sound wood. Let's now set up our calculations. The formula above is used to obtain the slope correction factor. With the table provided, we can determine that since our transects were on slopes less than 10%, our slope correction factor is 1. In this table, I have listed each variable required to calculate the total surface fuel loadings as the header. So far, we know that our constant is equal to 11.64 and that our slope correction factor is equal to 1. I also entered the number of total intercepts for each size class by summing the 4 plots together, summing the twig 1, twig 2, and twig 3 columns to get n. For fuels greater than 3 inches, we have to sum the squared diameters of each of the transects in place of n times d squared. For the 3 smaller size classes, the next variable we need to enter is the average squared diameter. Follow along and fill in the remaining columns over the next few slides. This table from Brown 1974 estimates d squared, or the average squared diameter values for different cover types by size class. The following abbreviations apply for species/cover. Type PP equals ponderosa pine, LP equals lodgepole pine, S equals Engelmann spruce, DF equals Douglas fir, L equals western larch, GF equals grand fir, C equals western red cedar, AF equals subalpine fir. All composite values are averages of non-slash and slash fuels with each cover type and species weighted equally. Since we are using a Douglas fir stand for our example, we need to use the DF values. For our calculations, we will use the non-slash values listed in this table. We also need to estimate S, the specific gravity, and A, the non-horizontal particle angle for each size class. Once again, we will use the estimates from Brown 1974. However, you could use local estimates from other sources for either of these. The top table is for specific gravity. To estimate the non-horizontal particle angle, we will use the bottom table from Brown 1974. We will use the values listed in the fresh slash column under Others for each size class. Once you have located these values, you can add them to your table. We also still need to calculate the total length for each sampling plane by size class. To do this, multiply the number of sampling planes by the length of each sampling plane. In our example, we sampled the 1 and 10-hour fuels for 6 feet, the 100-hour fuels for 10 feet, and the 1,000-hour fuels for 50 feet. Our sampling plane lengths will be 24 feet for the two smallest size classes, 40 feet for the 1 to 3 inch size class, and 200 feet for the fuels greater than 3 inches. Once you have finished entering your data into your table, we can use the two equations we previously learned to calculate the total fuel loading by size class. Now, calculate the fuel loading for each size class, the total fuel loading, and the average depth and litter depth. Average depth and litter depth, including twigs, are calculated by adding up all the observations and dividing by the number of observations for each one. For average depth, you should end up with 3.2 divided by 6 to get 0.53, and for litter, you should get 50.6 divided by 20 to get 2.18. This table shows the summary data for our surface fuel loading calculations on this stand. If you do not get these calculations, then please pause and review your calculations or use the PDF printout of this presentation to check your work. In many cases, we will sample in stands that have been treated and may contain slash piles. Although this class is primarily concerned with the techniques of estimating fuel loading and describing the fuels complex, we will cover how to estimate the particulate emissions from a pile. Guidelines for estimating biomass of piled slash were developed by Hardy, 1996. There are 6 steps required to form an estimate of particulate emissions. You must determine 1. Total gross volume of the pile, 2. Net volume of the woody biomass, 3. Density or weighted average density of the wood, 4. Consumable mass of the wood, 5. Proportion of mass consumed, 6. Mass of particulate matter produced. We will go through each of these steps in the next few slides. The first step in estimating the volume, biomass, and smoke production of a slash pile is to select a representative pile shape and calculate the gross volume. Hardy 1996 uses 7 different pile shapes. Once you have selected a pile shape, you can calculate its gross volume using a formula. Hardy provides the formulas for each of the 7 shapes he uses. Since much of the gross volume of the pile is occupied by air, the gross volume must be multiplied by a packing ratio to determine the net volume. The ratio of wood volume to total volume is called the packing ratio. Hardy suggests that the net wood volume can range from 6% to as high as 26%. Hardy also provided a few estimates for packing ratios based on the dominant species, the size of the logs in the pile, and how the pile was constructed. As you can see, piles dominated by ponderosa pine with mean diameters of large woody fuel less than 10 inches have a packing ratio of around 10%. Piles dominated by short needle conifers have packing ratios between 15 and 20%. Highly compacted clean piles with large logs have packing ratios of 25% or more. In step 3, select an appropriate density for the wood in the pile. The table shown displays the density for 14 common wood types in the western U.S. If more than one species is present, you can do a weighted average of the two species in the pile. Multiply the wood density by the net volume to get the oven dry mass or weight of the wood in the pile. Divide this value by 2,000 to convert to tons. At this point, we have calculated the weight of our piles and may consider these into our fuels complex estimates. The relationship between all of the variables mentioned is displayed in the monogram above. The percentage of wood mass consumed is typically between 75 and 95%. Hardy 1996 suggests that expert knowledge will be required to estimate this value, but several Western smoke management programs recommend using either 85% or 90%. Once you have selected a value, multiply it by the value calculated in step 4 on the previous slide, the consumable mass, to produce the total mass of the consumed material. The mass of an emission produced by a fire is calculated by multiplying the mass of the fuel consumed, which was calculated in the previous slide, by an emissions factor. The emissions factor is dependent upon the type of emissions you are interested in, PM, PM10, or PM2.5. The table shown from Hardy 1996 provides estimates for these three types of emissions. The emissions factor depends on the amount of soil mixed into the pile and the combustion efficiency. Once you have estimated the emissions factor, multiply the mass you calculated in the previous step by this value to get the amount of emissions for different sizes of particulate matter. Next, we will consider a hypothetical example using Hardy's method. Assume a Douglas fir stand has undergone thinning. As part of the treatment, we have 10 slash piles that were constructed by hand, resulting in well-rounded half spheres. Suppose each pile is 10 feet wide by 5 feet high and consists of 100 Doug firs. We estimate the packing ratio to be 20% and the consumption to be about 85%. Since the pile was hand-piled and is considered clean, we will use an emission factor of 0.9. Suppose we want to estimate the amount of particulate matter released during the burn for three size classes: total PM, PM10, and PM2.5. Let's go ahead and perform these calculations. The first step is to decide upon a shape to represent the piles. In this case, we will use a half sphere. Note that for a half sphere, the height will always be half of the width, because the height is the radius of the pile and the width is the diameter of the pile. The equation to calculate the volume of a half sphere is 2/3 pi h cubed. Using the formula, we get 261.7 cubic feet per pile. Next, calculate the net volume of a pile. The net volume is equal to the gross volume times the packing ratio. We calculated the gross volume in step 1, and we estimated the packing ratio to be 20%. Using the formula, we get a net volume of 52.3 cubic feet. Step 3 requires us to estimate the density of the wood. Our piles are made of 100% Douglas fir, so we use a density of 28.1 pounds per foot cubed. Next, calculate the consumable mass of the wood. To do this, multiply the net wood volume from step 2 by the wood density from step 3. In our example, we get that the net wood mass is 1,470 pounds, or 0.735 tons. This calculation tells us the weight of the pile, so if we were simply trying to estimate the fuel loading on the site, we can multiply this value by 10 to represent the amount of fuel in the 10 piles. Continuing, we can calculate the amount of particulate matter produced from burning the 10 piles. In step 5, we estimate the proportion of mass that will be consumed. Recall that we estimated fuel consumption as 85%, so multiply the net wood mass by 0.85 to get that an estimated 0.62 tons of mass will be consumed. The final step is to calculate the mass of particulate matter produced. To do this, multiply the mass consumed from step 5 by an emissions factor from the Hardy 1996 publication. For our example, we will use the following emission factors: PM equals 22, PM10 equals 17, and PM2.5 equals 14. Plugging these emissions factors into our example, we get the total emissions per one pile of 13.6, 10.5, and 8.7 pounds respectively for total PM, PM10, and PM2.5. Remember that this pile was representative of the 10 on the example site, so to get the total emissions for the stand, multiply the values by 10. In this lecture, you have learned two methods to inventory surface fuels. Using these two techniques, you should now be able to quantify surface fuel loadings in natural fuel conditions, slash fuels, and piled slash. As we move on to discuss other methods for inventorying surface fuels, I would like you to think about the accuracy of the estimates compared to the amount of time it takes to get the estimate. Also, consider what the estimate is for in the first place. Is it to predict fire behavior, emissions, for a wildlife survey, or some other reason?